Welcome to solving session for Introduction to Group Theory course. I am Siddhi Balu Ambure from IIT Gandhinagar, and today we will discuss problems related to syllabus from week 4, that is problems related to cosets of a subgroup of group and Lagrange theorem, some number theoretic application of Lagrange theorem and normal subgroups. Okay, so let us start with first question. So question 1, that when 34 power 82248 is divided by 83, then the remainder is A0, B1, C77, D37. So any guesses how we are going to proceed with this, or what is the approach which you will, because definitely we are not going to actually calculate what is 34 power this 82248 and divide it by 84. We have to do we need to use some results. Yeah, exactly, using congruence. So we have to use some results which we have seen in the lecture. So okay, so we have this so let P be prime, and say note that here 83 is prime number. Okay, 83 is prime number, and we have, if P is prime and for A belongs to Z, if GCD of A comma P is 1, then A power P minus 1 is congruent to 1 mod P. This is what we have here. Okay, and here also note that okay, so here my P is 83 and A is 34. So GCD of 83 and 34 is anyway 1, because 34 is 17 into 2 and here we have 83 which is prime. So GCD is 1, that's not a problem. So using this theorem, we so far have A power, that is 34 power this 83 minus 1 congruent to 1 mod 83. If I call this star, then using star. So we have 34 power 82, sorry, yeah, 82 congruent to 1 mod 83. Here also note that this number is 822248. Okay, so this power we need is, power required is 82248. Here we have 822. So what 82. So if I take maybe multiply it by 1000, then I mean I'm just I want to use this A, if A congruent to B mod sum M and C congruent to D mod sum M, then this both imply that AC is congruent to BD mod M. This is what I want to use. So what I need to do is I want to find like how many multiples of 82 can be accommodated in this number. So I want to find the multiple of 82, because here since here we have 1, this this on the right hand side it will still remain 1, doesn't matter how many times I multiply this 82. I mean if I multiply this equation again and again using this criteria. Let us call this one, this property of congruence. So that's what I want to do. So let us try to divide this by 82 and see what we get. And it is, of course, 1 will be there and 82. So 0, 0, I have 2, 4, 2, which is 0, again 4, we get 0, and 8, it will, if you check, it will be 3, and because 8 3s are 24, so yeah, it will be 246. So 2 is remaining. So I get 34, 82 whole power if I take 1003. This will be congruent to again 1 power 1003 mod 83, and this will give me 34, and this is 2 is remaining, so I get 34 power 82246, which is congruent to again 1 mod 83. Now I need to increase the power by 2, so let us see what is this 33 power 2 square congruent to. I mean, we need to find this number, what this is congruent to, 34 square. Okay, so let's, since this only is 2 power 2, we can simply do this 34. 34 is congruent to 34 mod 83, and 34 square is 34 square, you can check, it will be 1156. Okay, you can check this. And this 1156, when I divide by 83, it is 83, and it will be 236, and it is 3 249 and 77. So here I get 77 as my answer. So using this, if I call this 2 and if I call this 3, using again this star, using star on 2 and 3, I get 34 power 28848 congruent to 77 mod 83. Okay, so this is the correct answer. We just calculated it. So is there any doubt here? Please be careful the way you are multiplying this, the power, where it is getting multiplied, where it is getting added, and so on. Okay, this is what we got. And any doubts here? This was just simple calculation and nothing else. So yeah, if you still have any doubts, please let me know. Yeah, and no doubts. Okay. So let us move to next question. So let sigma be an n cycle in the symmetric group Sn, and then the index of the subgroup sigma, I mean, it is cyclic subgroup generated by this sigma in Sn is n minus 1 factor. Okay, so they are asking us what is index of the subgroup. So let us first understand what is index of a subgroup is. So the index of a subgroup in a group G is given by, of course, G is given by cardinality of subgroup H in a group G is given by this division, cardinality of G by cardinality of H, or order of G by order of H, and it is denoted by this square bracket G colon H, and this is also number of cosets H has in G. So understand that. And so they are asking us what is, so note that sigma is n cycle. So yeah, it is D, correct. So as suggested by someone, it is n minus 1 factorial. But how? So see, cardinality of Sn here is n factorial, which we all know. And for any n cycle in Sn or any k cycle in Sn, order of group generated by that k cycle is k. So here they have given us that sigma is n cycle. So the order or size of cyclic subgroup generated by this sigma will be n. So this is n. So therefore this index of this sigma, or let me write this index of this, is cardinality of Sn, or order of this group Sn, which is n factorial divided by n, which is clearly n minus 1 factorial. Okay, so this is what is asked here. So this was very clear. I mean, you do not need to put much. The only thing to notice here is that order of this cyclic subgroup generated by n cycle in Sn has cardinality or has order n. This was the only catch in this question. And the definition of index is here, but yeah, nothing else. I hope this was clear. Let's move to next question then. So question 3, let me write here only. Let G be such that every subgroup of G is a normal subgroup of G, then A. G is abelian, B, G is cyclic, C, G is non-abelian, and D is none of the above. So what they have given is that G is a group such that every subgroup of G is a normal subgroup of G. Okay, so what is normal subgroup? So if H is a subgroup of G such that for all H in H and for all G in G, we have GH G inverse belongs to H, then H is called normal subgroup, of G. Okay, so this is the definition. We want to check this whether this happens or not. So note that by the definition itself, one can see that in abelian group, every subgroup will be normal subgroup, because in abelian group, this G inverse will be what? G inverse H, because see, I can write this, right? This is G inverse H, and from associativity I can have again this, and this will give me EH, and anyway we started with the H in H, so H in H, G in G abelian. Then okay, so this happens. So for every abelian group, every subgroup is a normal subgroup. So in either I need to prove that G will always be abelian, G will always be cyclic, or G is always non-abelian. So what is your guess here? Do you think any of these three, that is abelian, G being cyclic, or G being non-abelian, any of this is true? If any of this is true, then we will have to prove it. And if not, then we have to give counterexample of each. So note that in this case, if we want to give counterexample for abelian and cyclic case, giving abelian as a counterexample would also, giving a counterexample for abelian group, that if we find a group such that it is non-abelian with every subgroup of G is a normal subgroup, then it would also discard the cyclic option, because every cyclic group is anyway abelian. So if it has to be cyclic, then it needs to be abelian as well. So uh, one non-abelian example will be enough to discard both of these options. And to have this that G is non-abelian, we can give any example, cyclic, abelian, doesn't matter. So do you think any of this statement is true, or we have to give counterexample for each of this? I mean, at least if we have to say that none of these three options is true, then we have to give counterexample, at least one being abelian group and one being non-abelian group. So any suggestions or any guesses, or do you think none of them is true? Okay, but do you have counterexample at least for this? That G is non-abelian. Do you know any group G such that it's every subgroup is a normal subgroup, but G is not non-abelian? That is example for this C, but I'm talking about, okay, I mean S3 is example such that it is non-abelian and it's every subgroup is of size either 2 or 3. And when I take quotient, uh, then we get group of size. No, that won't work actually. In S3, how do you calculate all the cycles? So you're saying this S3 is example of non-abelian group. So let me just tell you this. We have to discard this option. We have to discard this option. Uh, so let me just write this. Question, sorry. Let G is equal to simply take Z7. Okay. Z7 is cyclic and abelian, and every subgroup of Z7, that is only subgroups of Z7 is this 0 and Z7 itself, are normal. Therefore, G is equal to Z7, but Z7 is not non-abelian. So therefore, this is not true. Okay, so this one is not true, G being non-abelian. This is clear, right? Because we can take abelian groups where subgroups are always normal subgroups. And in that case, this option C is anyway wrong. G being non-abelian always if G is such that every subgroup of G is normal subgroup. Okay, so we have to now give counterexample for this abelian or cyclic group. So we have to give G such that its every subgroup is a normal subgroup, and G is not abelian. That's the example. So as suggested by so let us try with, so S3 is the example which you can try, but I want to give this example. This Q8, it is this group containing this plus or minus 1, plus or minus I, plus or minus J, plus or minus K. This is called as quaternion group. Okay. And it is such that, let me again give its description. This E bar. E bar means this minus 1. It is generated by these elements minus 1, I, J, and K, such that this, if we call it I, then I bar square is E. This is actually minus 1 square is equal to 1. And I square is equal to J square is equal to K square is equal to I, J, K is minus 1 here. Or this is just E bar by notation. Let me just write minus 1 here. Doesn't matter. Okay. This is group which we want to talk. And its size is 8. Okay. So all possible groups will have say size if H is subgroup of this Q8, then cardinality of H is either 1 or 2 or 4 or 8. Okay. And note that here this I square, J square, K square is minus 1. And since no other element, since order of group is 8, 3, I mean, no element can have order 3. And then when I take fourth power of any of this I, J, K, it will become 1 because I square is minus 1. So if I take square of it, it will be minus 1 square, which will give me 1. So 2 is anyway not the possibility. 3 again is not a possibility. So order of this I is 4. So order of this I elements I, J, and K, you can similarly check, is 4. Okay, so and it, as I said, every subgroup can have either size 1, 2, 4, or 8. The only possible subgroups are either of size 1. So 1 size 1 means only identity element, that is 1. So this is group under multiplication. So size 1 subgroup means only identity element. It is always normal subgroup. Okay, and second is this -1 and 1. So size 2 group, subgroup of size 2 is only this subgroup, -1 and 1. So this is the only group, this is the only possible group of size 2 here. And you can check that -1 commutes with every other element, and 1 also commutes with every other element. So this is actually center of this group, -1, 1. And therefore, it is the normal subgroup of, it is a normal subgroup. Just a second. What? Okay, no problem. It is a normal subgroup of Q8. So, is this okay? I mean, I hope you know this is, let me just write here, center of Q8. And you know, I hope what you all know what is, it is collection of all those x in G such that xg is equal to gx for all G in G. So it is collection of all the elements in G such that those element commutes with all the other elements of the group. Okay, and Zg is always a normal subgroup, because if I take any element x from this Zg and G in G, then Gx G inverse will be, since this commutes, xg is equal to gx for all. Again, the same argument which we had for abelian case, this will hold here, and x into E, and this x will again belong to Zg. Okay, so this happens with center of a group. Now, subgroup of size 4. So can you tell me the subgroups of size 4 here? All the subgroups of size 4. It will definitely be these groups, right? I generated by I. Can you see? This will be subgroup containing I square will be -1, I cube will be -1 into I, so that is -I. And again, I power 4 will be this -1 square, that is 1. So this is the subgroup which we have here. So similarly JK, are there any other subgroups of order 4? No, right? If you have, you can check. So far we know these subgroups of size 4, which is generated by these single elements. And so we will only check for this. We have to check whether this, let me call this I1, H1, this is subgroup generated by I, is normal subgroup in Q8 or not. Okay, is H1, that is normal subgroup in Q8 or not. Okay, we have to check. So what we have to check is, that is this GH G inverse belongs to H, whether for all H in H1, G in G, whether this GH G inverse belongs to Q8 or not. So can You guess whether this is true. So note that we have 8 elements in Q8, and the elements which are already in Q8, we need not check for those. Sorry, we have to check this G inverse belongs to H1 or not. So, and G has, this Q8 has 8 elements, and H has 4 elements. H1 has 4 elements. So I only need to check for elements which are not there in this H. So G I will choose from this group minus this H1. Because anyway, if I take this G from H1 itself, then H1, I mean the element. For example, if I take H in H1 and H1 G, H again the H in H1 and H dash in H1, then H1 H dash into H dash inverse will always be in H because of subgroup property that multiplication, it is closed under multiplication. So we will only choose elements which are not there in H1 in order to check this condition. So what are those elements? Those are this J minus J, K minus K. These are the only elements which are not there in H and are there in Q8. So let us check for this one. So I need for J, I will take J, I minus J. And again, also note that 1 and minus 1 also commute with every other element. So we again do not need to check for that. This, because in that case again this will have this, because elements from center commute with every other element of group, and in that case this will again hold. So again from H1 itself we do not need to consider this 1 and minus 1. So only remaining elements are this J, I and minus I, and we have to check with how I and minus I, when I multiply with this J minus J and their inverse, whether they land in H1 again or not. So this is J into I into minus J. So I didn't mention here, but I hope you all know that for this group, this I into J is K, J into K is I, and K into I is J. I hope I wrote correct. Yeah. And when I reverse the sign, it's minus of these elements. For example, J into I is minus K, K into J is minus I, and I into K is minus J. So I will use that. So J into I is minus K into minus J. So minus 1 is in center. So it commutes with every other element. So this is K into J. K into J is, no, it is minus I. And this belongs to H1. And note that similarly, this minus I minus J, again, I can take this minus 1 out, and this will be minus J I minus J, and this will be minus of this minus I, which we just calculated, and this belongs to H1. Now similarly, again, if I take this minus J, I and J, note that inverse of J is minus J, because J square is minus 1. So Simply j power 4 is 1, so j inverse is j cube and j cube is minus j. Okay, so minus j is the inverse of this element. Now I have minus j, ij is k. So, and minus jk is I, which belongs to h1. And similarly, if I take here minus I instead of I, then again minus comes out here, minus j, minus I, and j, I will get I in h1. Similarly, you can check for these other two elements. Do you want me to check or is it okay? I think you got the idea how to do it. You can check for, so let me just write the list of elements which you need to check. It is k, I minus k, k minus I minus k, minus k, I, k, and minus k minus I, k, whether this belongs to h1 or not. And you can see that all these elements belongs to h1. And similarly, you can do with this h2. You can take this cyclic subgroup generated by j. That is this group j minus 1, j cube, which was minus j, we just saw, and 1. And similarly, this h3, that is subgroup generated by k, that is k minus 1, minus k, and 1. You can also check for these two sets that when I take quotient, I get that this G, G, H, I, G inverse is subset of H for all G in G, and 1 less than equal to I less than equal to C, HI. Okay? Any doubts here? Even for the S3 as suggested by one of you, you can check for S3 also. And in case of S3, it has like subgroups of size 2 and 3, and you can check those subgroup generated by those 2 and 3 cycles, how they behave with S3 when we take this kind of multiplications. Okay, so any doubts here? So the answer to this question is none of the above, because we got counterexample for every. The moment I get counterexample for something being non-abelian, it can also be viewed as counterexample for something being non-cyclic. Because if something was cyclic, it needs to be abelian first. Okay, any doubts? No, okay. Let us move to next question. So this example, so this shows that A and B are wrong, are not correct. And this gives where not abelian, and therefore shows that C is not correct. So this is question 4, that which of the following subset are subgroups of C star under multiplication. First option is all those A in C star. This is complex. Multiplicative set of complex. So it is just C star as a set is just complex number minus this 0. That's it. And it is such that modulus of A is less than equal to 1. So I hope you know what this means. Let me just write all the options, then I will tell you what this modulus here means. This is not the order of element in the group. Okay. It is mm, it is the modulus of that element of complex number. Otherwise, this doesn't make any sense. Okay. This may greater than 1 and CH is such that A in C star such that and D A in C star such that mod A is equal to 1 union this mod A is equal to 2. So any doubts here? I mean, doubts means the question is here. Yes. So I wanted to say for A in C star. So A in C star means A is also in C. So A is from some x plus iy, where x and y are in R. So this modulus of A is the square root of this x square plus y square. And we take positive, positive square root of x square plus y square. Is this okay? So this is that a modulus which they are considering. So what they are saying here is that this H is a subgroup, not subgroup, subset of C star such that it is collection of all the elements such that this modulus of that A is 1 or less than equal to 1, greater than equal to 1, or A is equal to 2, and so on. So I hope the question is clear now. This is not the order of group. This is modulus of that element, that complex number in as defined like this. Okay, so any guesses which one is the correct option? Yeah. So let us see each option and let us try to see whether we get any counterexample or not. Okay, so let us start with option 1. So H is such that all those A in C star such that A is less than equal to 1. And note that here my G is this C star under multiplication, and identity of G is 1. Okay, multiplicative identity of this G is 1. So, and one more property of this modulus is, let me just shift this here. For A comma B in C, these are properties of C actually. Let me remove this altogether. Okay. So for AB in C, I have this modulus of AB is modulus of A into modulus of B. Okay, this is property which we have in general. Okay, so and this C star has identity like this. Okay, and modulus of 1 is just 1. I hope this is clear. So if I take, so let A is in C star, so I can very well take this A is equal to, give me some complex number. Complex numbers are also, real numbers are also there in this set. So I can just choose A to be half, right? Then this belongs to C star, and this is less than equal to 1. In fact, is half, which is less than equal to 1. Is this clear? So if this H was a group, its inverse would also exist in this set H itself. So if I have so if A inverse belongs to H, then modulus of A inverse would be modulus of 1, and this will imply that mod of A into mod of A inverse is 1, and then mod of A inverse would be this 1 by mod of A. This is here 1 by 2. So it becomes 2, and this is not less than equal to 1, which is property of this set H. So therefore this this for A is equal to 1 by 2 belongs to H. A inverse, which is 2, doesn't belong to H. And this 2 belongs to C star, okay? But this 2 does not belongs to my H. So therefore H is not a subgroup of this C star multiplication. Any doubts here how we are going about it? So we are given condition on modulus of element in complex set of complex numbers, and we are entirely playing with this using this property. Okay, I'm again highlighting this. This is really important, that if I take product of two complex numbers, then their modulus is again product of this their mod, and modulus of a product is product of modulus. Is this okay? So the second B part, can you come up with similar kind of argument for here, that A in C star such that mod A is greater than 1? Can you work with a similar kind of argument? Because if I take again, now since I want A in H with modulus of A greater than 2, I can similarly choose let A be 2. And modulus of A is 2 again, which is greater than 1. But if again A inverse belong to H, then this again 1 is equal to mod of A inverse, which is 2 into mod A inverse, and this is 1 by 2, which not true. So therefore again this H is not a subgroup of C star under multiplication. I hope this one is clear. It was a similar argument. I just chose A in H, which satisfies the property, and showed that its inverse again does not belong to the set H itself. Now the C is 2 C star such that mod A is 1. And as suggested by one of you, this is a subgroup. So how to prove that something is a subgroup? How do we proceed with it? So we claim that H is a subgroup of this. So how do we go about this? Any guesses? We know that, right? That we proved this long back, that this is anyway non-empty subset. So if H is a if is a subgroup of G, then if and only if, in fact, if and only if AB inverse belongs for all AB in H, AB inverse belongs to H. We will use this property. If you remember, we proved this in, I think, first or second live session. If you want, you can go and check the notes. It's available. We proved this. And we also saw that this H being non-empty is important. Okay. So let A and B belongs to my H. So what I have is that modulus of A is 1, modulus of B is 1. But note that since I want to work with B's inverse here, since B belongs to H, then there exists, and which belongs to C star. So this implies there exists B inverse in C star. C star is a group. Okay. C star is a group. I'm taking this B from H, which is element of C star, the bigger group. And now I have this B inverse in C star. I have to check whether this B inverse belongs to my H or not. So B inverse belongs to C star. So I have B inverse is equal to 1. So B inverse, which is 1 into mod B inverse, which is this. So this implies my B inverse belongs to H. And I wanted that. And the moment I get this, I have this AB inverse. This is modulus of A, modulus of B inverse. But since I got that modulus of A is 1, modulus of B inverse is again 1. We proved that B inverse is in H, and also modulus of B inverse is 1. So this implies this is just 1. So this AB inverse belongs to my set H. So therefore H is a subgroup of C star. Okay. So this is subgroup. Any doubts here? No, right? If you have any doubt, please let me know. Otherwise, we will move. Now the D part, which is this H is union of these two sets. A in C star such that modulus of A is 1, union A in C star such that modulus of A is 2. So can you give me counterexample? Like what we did here was using inverse, but here can you directly say something? Like what is happening? That this is not a subgroup directly without involving inverse. Note that here we have this set as well. So if I take A comma B in C star such that modulus of A is both, let us me write modulus of, inverse of 2 is okay. Again, because again inverse of 2 will have size half, and that modulus will be 1 by 2, which is again not there in this set. That is okay, but here it's even easier. If I take these two elements in H with this modulus 2, then what will be modulus of AB? It is 2 into 2, that is 4. And it is anyway not there in this set. The multiplication itself, there the inverse was the problem. Because see, if I take two elements here, if I take two elements with modulus less than equal to 1, their product will still be an element with modulus less than equal to 1. Similarly, so that's why we had to involve this inverse of that element. Similarly, if modulus of two elements is greater than equal to, not greater than equal to, greater than 1, their product will again have modulus greater than 1. So again, that's why again in this case I had to we had to involve A inverse to say that okay, A inverse will have size less than model less than what is, or greater than, compared to what is required for inverse to land in the set H. But here the multiplication itself is a problem. Again, the multiplication itself is not satisfying. The moment I take two elements of modulus 2, their product will have modulus 4. So here the multiplication itself is, this set is not closed under multiplication itself. So is 4, which does not belong to H. So therefore H is not closed subset. Close is not closed under multiplication. Hence, therefore H is not a subgroup of C star. Is this okay? Uh, like, can you understand the difference between the reasoning of this both the, it does not belong. Yeah, the both the problems. Earlier the inverse we had to involve because the product was still satisfying the condition which was there on H. But in this case, the product itself is failing. So we don't, again, inverse we can always use, but that's the problem. Product is not satisfying the condition before we even go to the inverse of the element. So is it okay? I hope you if please let me know if there is any doubt, like why we didn't use this condition in earlier examples and so on, or any doubts in general whatever we did so far. Not, then please go through. Meanwhile, I will write the question, and also you can try to read what I'm writing and try to find the counter examples or examples of this. Of the following are incorrect. We have to find the wrong statements out of the options. Let me write the options first. If for every positive divisor D of n, there exists a subgroup of G of order D, then G is cyclic. Option B is that if H is a subgroup of G, then the order of H divides the order of G. C is that if G quotient Zg is cyclic, then G is abelian. And the D part is that if G Zg is abelian, then G is abelian. So any cases for this, like which one is true, false, or whatever your guesses are. So yeah, we have to check which one are incorrect, or let us remove this. Let us find which one are correct. Doesn't matter whether we find for correct or incorrect. Okay, we have to check which one of these is correct. So any guesses? Which one of these is true, false? Any counterexamples or proofs? So this one is anyway true. Okay, this is statement of Lagrange theorem. I hope you all know this. It's discussed in the lectures that this is Lagrange theorem, that H is a subgroup of G, then order of H divides order of G. Okay, yeah. So this is true. This is theorem which is discussed in the lecture, and I hope you all have gone through the proof and so on for this theorem. Okay, if not, then try to prove this by yourself. If you have in doubt, please ask it in the discussion forum. We will discuss it there. But please try to understand the statement and the proof for this theorem. So so this statement itself is a Lagrange theorem. So we won't be, so this is true. That's there. We don't have to find any counterexample or anything. This statement is true, we know. Now about these other three options. What are your guesses? Which one is true? Which one is false? If it's false, what's the counterexample, or what are the counterexamples? And if it's true, then how to proceed with the proof? Which one of these A, C, and D you think is true or false, whatever your guess is? So A says that, okay, let us discuss one by one. A, that if for every positive divisor D of n, there exists a subgroup G of order D, then G is cyclic. So can we recall one example which was discussed earlier or suggested by one of you, which satisfies this condition but is not cyclic? Okay, so S3 we can take. G is equal to S. Definitely S3 is not cyclic. Is this clear that S3 is not cyclic? Okay, all the possible cycles are of size 1, 2, 3, and 6. N cycle of size, a cycle of size 6 will have order 6, 3 will have order 3. 2 will, I mean, the transposition or the 2 cycle will have size 2 and the identity permutation. So each element has either, I mean, these are the, I mean, if it was cyclic, it will be of these forms. So I hope you understand what I'm trying to say here. So therefore, but size of S3 is 3 factorial. So wait, we don't have any cycle of size 6 there, okay? Cycle of size 2 and 3, that's it. So this is with this. This is E 1 2 2 3 1 3 1 1 2 3 1 3 2, right? These are the only elements in this. And U, since G is 6, we can, and they say every positive divisor of D. So G is 6, so all the positive divisors of G6 are. So either it will be of size, so D has possibility 1, 2, and 6, 3 and 6. So for each divisor D, so for D I have this, for D is equal to 1, I have this, for D is equal to 2, I can take subgroup generated by any of the transpositions, and for 3 we can take any of these 3 cycles, or 2 3, doesn't matter. And for D is equal to 6, again my whole S3 itself is a group. There is no condition on the subgroup. It could be cyclic. I mean, they are not asking what is the nature of subgroup is, whether they want it to be abelian, non-abelian, and whatnot. They are just saying for every positive divisor D of n, there exists a subgroup of that order. That's it. And we here in S3 obtained that, but we know that S3 is not cyclic. S3 is not abelian, so forget about being cyclic. Okay, so S3 is not abelian, and hence, let me write here, and hence not cyclic. Therefore, option A is not correct. Okay, this is not correct. We just got the counter example. Counter example S3. And you can also check the counter example, the Q8 which we discussed earlier, that can also be used as a counter example for this. Because it was group of size A, the positive divisors were 1, 2, 4, and 8. And we just saw that for every divisor, we had subgroup of that size. For example, for 1, the identity is there, that's not problem. Then for 2, we had center of that group, that is not generated by, I mean the containing elements -1 and 1. For 4, we had those cyclic subgroups generated by I or J or K. Those were giving me subgroups of size 4. So that was also an example which can be used in order to say that this statement is false, that just because we have positive divides, I mean every positive divisor D of n, if we have subgroup of size D in G, then G need not be cyclic. We just saw 2 examples. Okay, and what about this statement that ZG is a cyclic, or G mod ZG is cyclic, then G is abelian? What is your guess for this statement? C. Let me just write C here, that if G mod ZG is cyclic, then G is abelian. Any guesses whether the statement is true, or you can find any counterexample? Or no guess? Can you give me counterexample? If if you want to say that it is okay in S3. In S3, what is the center of group? G is equal to S3. What is ZG? Yeah, the moment I take, quotient with respect to any non-trivial subgroup in S3, of course, the only possible subgroups are of size 2 and 3. And the moment I take this, it has size 2 or it has size 3. And by the cardinality itself, we can say that order is prime. So we can say that they are all cyclic. That's okay. But G is not abelian. That is also okay. But here I need G by ZG to be cyclic. These are ZG. ZG in S3 is only this, the identity permutation, or this E, if you want to write like this. We write this. ZG of S3 is so in that case, G mod ZG is again G itself, and it is not cyclic first of all. Let me write here ZG. So we can't use that as a counterexample for this statement. In fact, we can't use this as a counterexample for this statement as well. We want G by G mod ZG to be cyclic for this at least. So you have any counterexamples, or you now feel that it is true? Okay, so let me just say this, that this statement is actually true. Okay, and we'll try to prove this. So let us prove this, that proof. Let me write the statement again. So if G mod ZG is cyclic, then G is abelian. Okay, this statement is true, and the proof, let me write here, theorem, maybe this theorem, you can always use this. And what they have is that let G mod ZG be a cyclic group. Okay, then there exists GZG. We'll talk it with respect to, let us, I know you understand what this means. This GZG is in quotient. We are writing it to express element from quotient. You can also write this like this, but it doesn't really make any difference. So there exists GZG in G mod ZG such that this G mod ZG is this. Is this true? Is this understandable? I'm just choosing, not choosing, I mean, since it's cyclic, there will be some G such that this GZG will generate this subgroup, G mod ZG. So if I take, so if we take, so let H belong to G, then this ZG belong to this G mod ZG, right? So this imply, but this HZG belongs to G mod ZG, which is cyclic group generated by this GZG. So this implies this HZG is a G power M ZG, okay, not this, for some M or N doesn't matter. And so this, just this, by multiplication in quotient, we have this. I hope this is okay with you, right? I mean, in quotients, AH, BH, let me write here, in G mod H for AH, comma BH in G mod H. AH into BH is ABH. Okay, so just using that here. So if I do this, you will get that this GZG power M is just this G power M. So this imply H ZG is equal to G power M ZG. Okay, I just rewrote it. Don't need to. So this imply by quotient property. So the moment I have this H ZG is equal to G power M ZG, by quotient property, this G power M inverse H belongs to ZG. Is this true? That's the property of quotient, right? So these imply there exists I in ZG such that I is equal to this. I mean, I'm just renaming this element here like this. So this H which we started here is what? This G power M into this element I, where I is in ZG. So what I did, I started with the G, some element H in G, and with respect to this G here, this GZG, I'm trying to see like how that element H looks in my group G. So every element H of G is of this form, G power M I, where this I belongs to ZG and this G is a generator here, which is now fixed for now. The moment I chose that GZG is generated by this G quotiented by ZG is generated by this GZG, this G is now fixed. And for every element H in my group G, I get this, that it is of this form, G power Mi, where I in here. So note that again, initially we do not have this information, but we can write this. Once I have this, it is G power Mi, which is equal to H, but I is in ZG. So I can commute and I can write it as I. Yeah, I mean, yeah, that's it. This G power Mi is I into G power M, since I is in ZG. This you can keep in mind. This has nothing to do with H, but yeah. I mean, yes, H is this, and both the expressions make sense. So we started with any element H in group and we ended up getting that it is of this form G power Mi, G power for some I in Zg. So let H1, H2 belongs to G. Okay, and by our this expression so far, so let me just write here explicitly. Therefore, for any H in G, H is of the form M into I for some M in Z and I in ZG. Sorry, ZG, center of my group G. So therefore, let H1, H2 belongs to my G. And we claim that H1, H2 is equal to H2, H1. Okay, so since H1, H2 belongs to G, this implies this H1 is H1 is G power M I1. Let me just write M1 here, N1, since we will be writing I1. And H2 will be some G power N2 I2. If you have any doubt, please ask. Okay. So what is H1, H2? It is this G power N1 I1 into G power N2 I2. And what we can do now? We have this, right? H1 I1, since group associativity of the group, we can do this. And since this I1 is in center, it commutes with this N2 as well. Okay. So since I1 belongs to ZG, we can write this as Gn2 I1 I2, and this is G power N1 G power N2, and this I1 I2 doesn't matter, and this is N plus 1 N1 plus N2, and this is I1 I2 doesn't matter. Is this okay so far? N1 plus N2. But now the moment I have this N1 plus N2, I can split them and I can this write Gen N2 plus N1, this I1 I2, and this now becomes N2 G power, not G1 here, G power N1 I1 I2. Is this okay so far? So I started with H1 H2 and I got this expression of, note that this G power N1 G power N2 was G power N1 plus N2, but here I can write it as G power N2 plus N1, and this is giving G power N2 into G power N1. Okay, this please understand. This is just power of G, so I can just split them and it won't change or it won't affect the I mean, we do not need to invoke the G being abelian or anything. This is just property of an element. Its power we can powers. It is like consider them as inside cyclic group generated by G of G, not G by ZG, and this still holds. And now we have this, and now let us try to express this as okay. So far we have this H1 H2 is equal to G power N2 G power N1 I1 I2. Okay, and now I can again switch them. Since I1 I2 belong to ZG, I have this G power N1 I2 I1. Since I1 comma I2 belongs to ZG. So this implies that G power N2, and now I can combine these two, G1 N1 I2 I1, and this will give me N2. And now I can commute this again, because again since I2 belongs to ZG, I'm again writing again and again writing all the reasons because these notations can confuse. So, and this is what? This g power n2 I2, g power n1 I1, here it was I1. This was my H2 and this was my H1. So we started with H1, H2 and we ended up getting this expression here, H2, H1. And H1 and H2 were arbitrary from my group G. And I got this, that H1, H2 is equal to H2, H1. Any doubts here? Therefore, since H1, comma H2 in G were or are arbitrary, and we got that H1, H2 is equal to H2, H1. This implies that G is abelian group. Okay. Here we need not even use G being finite order or anything. Our G by ZG has finite order or nothing related to order of group G or order of G mod ZG. We just need the information that G mod ZG is cyclic. That's it. It could be finite, it could be infinite. We do not care. The moment I have G mod ZG, a cyclic group, then we can conclude that G is always abelian. We just proved it. Any doubts here in the proof? Anywhere something which no, right? Okay. So now the next question. Now the D part. We also need to discuss the D part of this statement, which is that if let me check, if G mod ZG is abelian, then G is abelian group. Is this true? Is this false or any counterexample? Yeah, any counterexample or proof? We are okay with anything as long as we can prove or give counterexample. Can we think of any group where G mod ZG is abelian? Note that here it's not any group. It's we need to have the center of that group G. So note that when we are trying to find counterexample for this one, we have to or we need to look for a group G which has non-trivial. I mean, if we are trying to find a counterexample, we need to look for a group which has non-trivial center. Because if you choose a group which has a trivial center, then G mod ZG or this G quotiented by ZG will again be group G, and it won't be abelian. Or it yeah, because if it was abelian, whole group would have been ZG and so on. So G quotiented by ZG will again be G, and it is not abelian since center is trivial. Okay, so when we want to find a counterexample of this kind of statements, where you want G mod ZG to be abelian, but G need not be abelian, you need to look for groups where ZG is not a trivial. Because let me write that. To find the counter example of this statement, we need to find a group with non-trivial center. That is non-trivial center. Okay. And as since if ZG is trivial group, then G mod ZG will be isomorphic to G, and this is not abelian, and it would not, it will not satisfy the assumption needed for the counterexample for the statement. We have to look for a group with non-trivial center. Can you come up with a group with non-trivial center? Any group which we discussed earlier which had non-trivial subgroup, if you remember, we discussed not many, but we discussed a few groups today, and one of them had non-trivial subgroup. So can you see there whether we can find any counterexample or whatever we want? Okay, so we discussed Q8 if you remember. Okay, and yes, exactly. Q8 and Z of Q8 was? Z of Q8 was this 1 comma minus 1. Non-trivial. Okay, so when I say this, this need not work when at this moment when we are, when I said this, it does not, I mean, for Q8 it is happening, but in general, even if we take G mod ZG, the resultant group need not be abelian again. In this case, we will be getting an abelian group, but that need not hold in general. Try to think of an example or try to prove it that G mod ZG is always abelian or something of that sort. Okay. So we have this, and Q8 quotiented by ZQ8 makes sense because see, ZG is always a normal subgroup of given group. So this makes sense. And what is cardinality of this group? This is this, right? We know. And it is 4. It has to be 4 because, yeah. So from here itself, can we conclude anything about this quotient being abelian? Or you want to see how the elements here look like? So Q8 mod ZQ8, let us write how the elements here are. So all the elements from here are gone. So note that I ZQ8 is equal to minus I ZQ8, if you remember, because if I multiply, it will give me 1 which is inside. So it has this IQ8, and what are the other elements? J ZQ8, KZQ8, and ZQ8, which is my identity 1 and 2. And what can you conclude from this? Is this cyclic? Or, I mean, let us see. So when I multiply any of those two, I ZQ8, J ZQ8, what is this? Okay, so if you do not know what is happening when I wrote this, please let me know. Why these are the only elements here? I assume you know what exactly happened here. Please, if not, please write it in the chat that you need to know how I wrote this. If you are not, if you not say anything, I will assume that you know what is happening here. It's okay. I assume that it's okay with others also. Okay, let me just quickly tell you. So if I try to write all the 8 elements, note that 1 and minus 1, I mean, we know this, right? AH is equal to BH, then AB inverse belong to H. That thing. So note that if I take IQ8 and minus IQ ZQ8, then this I and minus I are inverses of each other, and ZQ8 which is just 1 into ZQ8. So this in fact belongs to ZQ8, which is 1 belongs to ZQ8. Similarly, this happens with Z, K, and J and K. So that's why only, so this, if that's why instead of writing this IZQ8 and JZQ8 minus IZQ8, we in the quotient group, they two coincide. And I only get this one equivalence class here. Is this okay? Similarly with J, you can check, and K. And this 1 minus 1, this is entire my center of a group. ZQ8 is 1 minus 1. So this has two elements. This equivalence class has two elements, namely I minus I. This has two, J minus J. This has two, K minus K. And these are four equivalence classes I get when I quotient Q8 by ZQ8. Okay, so I hope this is clear. Let me keep this if somebody needs. Yeah. So yeah, I have this IZQ8 is equal to JZQ8. Or since these are four elements, let's try to write the product. So ZQ8, this, if you remember, IZQ8, JZQ8, and K, let me shrink this one. JZQ8, KZQ8. And similarly, if I take this, we are just writing the multiplication table for this Q8J ZQ. Let me just leave here. And ZZ, again, I will get ZQ8. Here, I into Z into I. Again, these are all identity elements. So this will remain as it is. ZQ8, JZQ8, and K. I mean, I'll just write it here. These are as it is. Now, I into I will be I square. Okay, and I square will be -1. And the moment I have -1, it will be, I mean, this minus ZQ8 is my ZQ8, right? -1 ZQ8 is my ZQ8 under this quotient. So this is my ZQ8. Similarly, here also, I will get this ZQ8. Similarly, for K square, again, I will get -1. And this is equal to ZQ8. And now these things, I into J was my K, if you remember. So this is my K ZQ8. And I think now you got the idea what exactly is happening here. Now again, J into I was minus K, but minus K is my K in this quotient. So it is again K ZQ8. So can you tell me what kind of group this is of size 4? Now again, I into JQ8. I into K was minus J, but it is ZQ8, JZQ8. JK was I, JK was I, ZQ8. Do you remember any group of this kind? J, ZQ8 and I, ZQ8. This is K4 group, if you remember. Let me just copy this. So which is we know is abelian group. So therefore Z not Q8 quotiented by ZQ8 is isomorphic to K4, which is abelian. From the group, from the table itself, we can say that it is abelian. Okay, so it is abelian group, but Q8 is not abelian. Okay, we know that Q8 is not abelian because Ij is not equal to Ji. Or if I want to write Ij is minus of Ji, whatever suits you. Not correct. Ij no is equal to minus Ji. That is Ij not equal to. Okay, so any doubts here? Like how, first of all, please understand how this quotient group is formed, then how the multiplication works there. And we saw that this is isomorphic to this K4 group, which is abelian group, which we know. But Q8 is not abelian. In general, I mean, the first, a group of size 4 is always abelian. The first non-trivial, first non-abelian group is S3, which we get. It needs to be of size 6 for us to have a non-abelian group. For example, size 2 group, abelian 3, abelian and cyclic. In fact, 2, 3 cyclic groups. For 4, we got this. For the first non-cyclic group comes with order 4, that is this K4 group, and the other is Z4. So order 4 groups are either isomorphic to Z4, which is cyclic, and if not Z4, it is a isomorphic to K4, which is abelian group. So order 4 groups are always abelian, either cyclic. In that case, that is isomorphic to Z4, and if not cyclic, then it is isomorphic to this abelian group Q4. Again, for size 5 group, we have Z5, which is again prime order group and hence cyclic. And now then we come to 6, and then there we have different kind of groups. Okay, so we have this S3, we have Z6, so which is cyclic, and this is in fact non-abelian, and so on. We can also have abelian groups of order 6, non-abelian groups of order 6, cyclic group of order 6, and so on. Okay? Is this okay? What I am trying to say here? Now this is the question here. We can try this question. That consider, I hope this is question 6. I don't remember. Okay, so since we are here, note that this one is correct and this is not correct. We give counter example. Wait. So see, I mean, many examples or questions which we solved today, Q8 was a counter example which we used. So try to remember this group if you are giving exam or in general when you solve assignments and whenever you study groups in general. Quotient group Q mod Z, then which of the following is correct? Okay, first A, for any n in Z, there exists an element in QZ, again this quotient, whose order is n. B, every coset in Q quotiented by Z contains exactly one representative Q in Q such that 0 less than equal to Q strictly less than 1, and C is that this Q quotiented by Z, this group is isomorphic. So note that this Q and Z which we are talking about, all these groups are under addition and Q is abelian under addition. Therefore, this Z is, in fact, in multiplication also it is abelian. I mean, with standard multiplication and addition, that's not a problem. But this Q is a abelian group under addition, and that's why the Z, which is subgroup, is normal there. That's why this quotient makes sense. So first of all, understand whenever someone writes quotient of a group, please understand that the group or subgroup with respect to which we are taking the quotient, please check whether it is it is normal group or not. It is really important to make sense of the multiplication in that new quotient group. Okay, so here the quotient makes sense because Z is normal. And it is Z in complex such that Z power n is 1 for some n in Z plus. And when I write this, it is under multiplication. Because under addition, this doesn't make sense. I mean, here we have addition, but here we have multiplication. Okay, that's what I'm saying. Here we have addition, here we have multiplication. I mean, it has to be multiplication here because if not, then if this was with respect to addition, then Z power n addition, then 0 must have been here, but that's not true. So this is not under addition. Please understand. These are small details, but are important when we try to solve these questions. I mean, to make sense of what we are writing and doing. Okay, so any guesses which one is true? So let us start with first. We are running out of time, but yeah, we will start and see. First, okay, so for any n in Z, there exists an element q by Z whose order is n. So can you give me such element whose order is n for any given n in Z in q quotiented by Z? And when I say q quotiented by Z, note that here this m by n Z is equal to, let me write m1, m2 by n2 Z. This implies this m2 by n2 minus. So this is m1 by n1 minus m2 by n2. This belongs to Z. Okay, that's how it is defined, or I hope you understand what I mean here. So I want n in, for any given n in Z, can you produce an element such that, and note that when I do this, the moment I get subtraction as integer, it becomes 0. So if I want to write, and the 0 here is 0 plus Z. Okay, under addition, we are in, let me write this. We are dealing with q comma Z under addition. Okay, and so identity is Z. And when I write this, this is 0 plus Z. And when I say 0 here, the moment I get integer after subtraction, I get that element belongs to Z and so on, whatever. So I want an element whose order is n. Can you give me one element whose order is n under addition in q mod Z? So let me write for n belongs to Z. Let us try with natural numbers. 1 by n belongs to q, 1 by nz belongs to this, right? And and if I add it n times, this 1 by n plus z, if I add them one n times, this belongs to, wait, not this. I want to write that this 1 by n plus z plus 1 by n plus z is again n by n plus z, right? This is 1 plus z, and which is z. So therefore, order of this is exactly n. You can't reduce the order. I mean, for any n less than n, for any m less than n, this, if m less than n, there's this m by n will always be less than 1. And since we are choosing this m to be here, then this will always be like this. So this has to be at least, we have to add it at least n times in order to get this one, to get this to be 0 of my quotient. So therefore, order of 1 by n plus z is n, and this n was any trivial in my natural number. So for all n in z and n greater than 0, right? Yeah, n in z plus. We were already asked for n in z plus. So that's we prove. That's what we prove. Even for negative, not negative, I mean, negative order doesn't make sense, but yeah. So I hope you are clear with this, that 1 by n, if I choose, it will be a group of, no, it will be an element of order n. Okay. And now other B part is every coset in Q mod Z contains exactly. So let me just copy paste it from here. Let us not waste time. We'll discuss this and see. So every coset in Q mod Z contains exactly one representative Q quotiented by Q such that it is between 0. So for 0 Z it is there. Let us consider any m by n in Q quotiented by Z. Okay. So let us take this 15 by 7 in QZ. What will you do in this case? I'm just trying to let us just try to understand what exactly we want to find a representative for this in this set. Can you come up with it? See, for 0, we are discarding 0. Okay. The moment I have this, what I will do is, I will, since if forget about this 15 by 7 in general, I have elements of this form here, m by n z in QZ. And this I consider non-zero. So this m by n, I mean, so when I say this is non-zero, this means that n does not divide m. This is clear? M can divide n, that's not a problem. Or it cannot. Yeah, m can divide n, that's not a problem. But I do not want m dividing n, because in that case, this will be some integer and it will be 0. So I'm taking non-zero. So the moment I have this kind of expression, and note that if m less than n, then anyway this m by n, 0 less than 1, and we get this expression. Okay, but if I have this m greater than n, then this m by n, what I will do is I will divide this m by n. And since it is not dividing m, there will be some remainder. And that remainder here will be of this. That remainder by 7, or sorry, the remainder here, let us take r, this r by n plus z, this will be my representation for this m by nz. R is such that r is, so m is equal to qn plus r. Okay, and 0 less than r less than n. And this will give me the expression. And why this makes sense? Because see, this m by n minus r by n is what? It is qn by n, right? Using this. And this is Q and hence it belongs to Z. So this actually makes sense. This M by N plus Z is actually equal to this R by NZ in my quotient group because this is happening. Please understand this, that this actually makes sense and this is the expression. And we cannot have any other expression because this expression which we get using using division algorithm, and the moment we restrict this 0 less than R less than N or less than equal to, doesn't matter. The moment I restrict this expression becomes unique, and that's why I get this unique R here. And that R by N will give me the unique expression of this any element M by N here. I hope you understand what I'm saying is this uniqueness is there exists exactly one. This uniqueness here is coming from the uniqueness of this R from here division algorithm when we are restricting between 0 to N. And this holds because we are assuming the division algorithm and we are saying that this N does not divide M and so on. I mean, you can properly formulate this and understand that this expression is unique, and this is how we will get this R, this element between 0 and 1 to represent this element Q in this Q mod Z and so on. Is this okay? So every coset will be of this form, and for every coset will be of this form, right? Q mod Z. And we got that this Q can be expressed, Q can have this form R by N, and we obtained it. Is it okay? Is it understandable? This Q which they are written here, Q is M by N for me, and I just proved that it will have expression of this Q. Q mod Z is actually R by N Z. QZ is R by NZ with 0 less than equal to R by N. Is this okay? Any doubt? Okay, it's okay, right? Great. And I think we are running out of time. But you can check that this C part, that this Q quotiented by Z isomorphic to Z belongs to complex such that Z power N is 1 for some N in Z plus. They are actually isomorphic. Okay, you can obtain isomorphism from this Q to this C star such that quotient is Z. Or you can just try to obtain a map or any kind of expression, and you can prove this, that this I mean, just since we are running out of time, understand that this statement is true, and try to find the map from this set to the other and try to prove that this actually forms isomorphism and so on. Is this okay? So the correct answers are all these three. This A is correct, B is correct, and C is correct. I'm marking this as star since we didn't prove it. And understand that this multiplication set, multiplication group, this you can also write C star. It won't affect much. Okay. And here N is in Z plus. So any doubts? Apart from this one, we can discuss this in next lecture. But for now, because it will take some time. So any doubts other than this star part? Let me just try. Whatever we did, how the quotients were, and Q weight group, and anything in general. If not, then we can stop for now because we are anyway ahead of time. And also, if you have any doubt, please raise it in the a discussion forum. We will try to solve them, and if not, if there are no further question, we can end the meeting. Okay, thank you. If you have doubts, please ask. Otherwise, I will end them. Okay, no. Okay, thanks.